Well, in the previous lecture, I have considered various aspects of deep excavation, and the main thing is that the finding out the start loading, and that much we try to do in this course. So, here I have shown how to analyze that and what are the different pressure diagram, etc. And now I will try to take one numerical problem to show how we can arrive the solution. So, let us take the problem. This is the problem actually shown. You can see that is here actually there are depth of excavation is 12 meter total, and there are 4 starts are given, and at a vertical spacing of 3 meter. You can see 3, 3, 3 and top 1.5, bottom 1.5, and one more is the start spacing at 4 meter center. So, that means perpendicular to the board, if I consider the continuous excavation, then this starts at there again another 4 meter interval. So, then while calculating load, actually influence area you have to consider. That means, I am considering while calculating start load, I will be taking from here to here this much vertically. Similarly, I have to consider horizontally also 4 meters. So, 2 meters from this side, 2 meters from other side. So, 2 meters from this and 2 meters behind. So, that means another 4 will come. So, to find out the start loading, this is the thing you have to consider actually the vertical spacing, to consider that means zone from half the zone of the loading will come to this, half the zone loading will go to there. Similarly, this half coming here, again this half will go there. Similarly, this half will come here and this half will go there, again this half actually is coming here and this part will come here, because there is no other support. So, like that vertically we are taking that way, that 50% this side, 50% other side. Similarly, when there is a horizontal that is a spacing is there laterally. So, that at 4 meter interval, that means for each start will be considered 4 meter width. So, that another 4 will come. So, that one has to keep in mind. So, that these are the things that is the geometry. If I could have done 3 dimensional, then this wall could have been continuous, I could have seen perpendicular to the board. And soil type given for this problem is actually soft to medium clay, and gamma is 17.29 and QU unconfined compressive strength actually 96. So, QU actually in our calculation we have seen that C value is required, but you know that Q is given. So, when QU is given, QU is 96, and relationship between cohesion and QU is C is cohesion QU by 2. So, that means 48 kilonewton per meter square. So, that is one thing is given, and soft to medium clay it is mentioned, that means we have actually shown 3 different pressure diagram. That means, based on this description we have to choose one of the figure. So, 3 figures, one is complete rectangle, one is top portion linearly varying, then remaining rectangle, then third portion third type actually it is top 1/4 is linear and increasing to maximum, and bottom 1/4 actually from maximum linearly decrease to 0. So, that 3 out of the, so this description, from this description we will be able to pick up the appropriate pressure diagram. And you can see that a braced sheet pile wall for an open cut in soft to medium clay is illustrated in the figure. That is the thing I have once again I have discussed. Starts are spaced longitudinally at 4 meter center to center. That means, vertical spacing is shown, longitudinal spacing actually 4 meter, and the sheet piles are pinned or hinged at start levels B and C. That means, your A, B, C, D already method of analysis I have mentioned that it looks like a continuous beam, but intermediate support can be considered as pin. Here itself it is also mentioned here itself that at point B and C we can assume that pinned or hinged, that nothing but what I have already told, and draw the lateral earth pressure diagram for the braced sheet pile system and determine the loads on starts A, B and C and D. So, this is the problem. So, based on the given description, so let us see first the different types of pressure diagram. You can see this pressure diagram we have discussed in the previous lecture, and you can see here that for sand this is the one, and for stiff clay this is the one, and for soft to medium clay this is the diagram. So, that means our problem is appropriate to this diagram. Okay. So, we have to pick up this, and now based on this, first of all you have to draw the pressure diagram, and then you have to find out the loading in the start. So, let me go to that next slide. So, next slide I have kept blank, and in fact, I will draw first and then I will do that. You can see here total 12 meter, and your one-fourth will be so this is the diagram. And here actually this is 1.5, this is 3, this is 3, this is 3. Okay. And this is also 3. Okay. And if I consider hinged here, hinged here, hinged here, then I can break this. The first one will be diagram will be like this, and the second one, so this will be F A, and this will be A B 1. Next will be A B 2, and this is F C 1. This is F C 2, and so this will be, this is suppose F D, and this will be actually 4.5, this is 3 and this is 4.5, this is 3 and this is 4.5. So, like this. So, now I can take actually intensity I have to find out, this intensity I have to find out, this intensity will be gamma h minus 4 c, and c already I have got q u by 2, that will be 96 by 2 actually 48. Okay. And p will be equal to 17.29 multiplied by 12, 1 minus 4 multiplied by 48 divided by 17.92 multiplied by 12, that gives you a value 15.48. So, that means this is actually 15.48. Okay. And if this is 15.48, and then if I take moment with respect to B, so this one for this problem, this is the 1 and this is 2, and problem 3. For problem 1, if I take sigma m b equal to 0, and then you will get half multiplied by 15.48 multiplied by 3 multiplied by 4. These become actually the total force on this beam. this force on this beam, and then I have to take moment with respect to this. So, I have to find out I have taken this triangle only. First of all, I have taken this triangular loading, the two we can divide in two parts. This is 3 meter, this triangle is 3 meter. So, that is what we have taken, half multiplied by 3 multiplied 15.48 multiplied by 4. So, that loading. So, I have to multiply it by lever arm, and that lever arm will be 1.5, this is 1.5 plus this is 3. So, 3 multiplied by 1 by 3. Okay. So, this is, that means its point of application was somewhere here, from here to here actually 1.5, this distance is 1.5, this is not shown proportionally. So, this distance is 3. So, half of that actually 1.5. So, this is the lever arm, and then I have to take this diagram. So, this diagram actually plus 1.5 multiplied by 15.48 multiplied by 4 multiplied by that is actually this become loading on that rectangular portion. So, this is 1.5 by 15.48, this is pressure, and because of the longitudinal spacing force. So, that I have to taken the total load, and then lever arm will be 1.5 by 2. So, it was 1.5. So, it will be from here to here, it is half 1.5 by 2. So, if I do this and then minus actually your F A multiplied by this distance between this is 3. So, that will be 0, and if I based on that I will get F A will be equal to 100.6 kilonewton. Okay. And F A if you are getting, then I will get F B 1 I will get actually. So, F A plus F B 1 F A plus F B 1 will be equal to summation of this triangle diagram. So, half multiplied by 3 multiplied by 15.48 multiplied by 4 plus 1.5 multiplied by 15.48 multiplied by 4. So, from here I will get F B 1 will be equal to 85.2. Now, if I go to this, and then it will be F B 2 and F B 2 equal to F B 2 equal to F C 1, and which will be equal to the area of this triangle but divided by 2. So, this is 3 multiplied by 15.48 multiplied by 4 divided by 2, that is nothing but 92.9. Okay. And next one for this problem number 3, sigma m c if I take 0, that means if I take moment with respect to this is d actually. So, it will give you F d multiplied by 3 minus 4.5, this is actually this length is 4.5. So, 4.5 multiplied by 15.48 multiplied by 4.5 by 2 equal to 0. If you do this, then your F d become 209 kilonewton, 0 kilonewton. So, we have got F A, we have got F d, we have got, and F B 1 you have got, F B 2 also you have got, F C 1 you have got, and F C 2 can be obtained, and from here actually once you get F d, and your F C 2 plus F d will be equal to nothing but your 15.48 multiplied by 4.5 multiplied by 4. Okay. Here actually there will be a 4, it has to be multiplied by 4 also, there will be 4 also here. So, this if you do from here actually we will get F C 2 will be equal to 69.6. Okay. So, now you can see your value of F A, your F A become F A already we have got how much 100.6, F B equal to F B 1 plus F B 2, and if I do that then we are getting 178. Similarly, F C will equal to F C 1 plus F C 2, and that gives you ultimately 162.5, and F D already known, actually you have got here 209. So, this is the actually total, it is very simple actually based on given pressure diagram, based on the given soil type I have to adopt the typical pressure diagram, and based on the start location I can divide into 3 beams like this, beam 1, beam 2, beam 3, and beam 1 and 2 actually 2 unknowns. So, we can take moment with respect to any one of course, but we can take with respect moment with respect to this one, then actually we will get directly F A. So, that is the thing we have done first, and once you get F A, F B can be obtained because summation of vertical force equal to external load, summation of vertical force will be 0, that means this reaction plus this loading should be equal to 0, that is done here, and from there we got F B 2, F B 1, and for second beam actually you can see it is a symmetric. So, because of that F B 2 and F C 1 must be equal, and if it is so, then what is their value? Their value will be total loading divided by 2, that is the thing you have done here. And then last beam actually again we have taken moment with respect to C, and then moment with respect to C if I take, then I will get F D directly, and once you get F D, then F C 1, F C 2 plus F D will be the loading here. From there we have got the F C 2, okay. Somewhere we have done F C 2 I have got, and then as I have shown before, F A itself whatever you have got, F B will be equal to F B 1 plus F B 2, that is the thing I have done here, and F C equal to F C 1 plus F C 2, that is the thing I have done here, and F D whatever you have got. So, these are the forces in the different starts already obtained. So, this is the way actually problem can be done. So, if it is instead of this diagram, if your if the soil would have been something else like same thing, suppose same 12 meter depth, and your if it is sand suppose, then we could have done pressure diagram something like this, and your start location was here, here, here and here, and then accordingly you have to divide into different parts. This is one part, this is another part, and so part 1, part 2, part 3, or if it is instead of saying this is actually what? This is actually steep clay. When it is steep clay, and if it is sand, then we could have considered something like this. This is the one, and your pressure diagram will be something like this, and your start location something like this. So, pressure diagram like this. So, this is simplest actually, we can divide into one part, second part, and this is the part 1, 2, 3, everywhere same, and it is part 1, part 2, part 3, and like that one can find out what is, and at this point we can consider the hinge, then we can find out what is the loading in the starts. Okay. So, with this we have almost at the end of the foundation engineering for all type of static loading, and in fact, as I have mentioned that I will take some amount of in the different examination nowadays in foundation engineering, there is another part is included, that is for dynamically loaded foundation. That means, so far whatever we have done, actually it is static loads are considered, and based on that we have seen bearing capacity calculation, we have shown the settlement calculation, we have shown pile foundation, their loading, settlement, then we have done for retaining wall also for static loading. Everywhere we have considered static loading only. So, now I have another 8 modules actually total, like that means 4 hours approximately, and try to give some introduction on machine foundation, that means or some dynamically loaded foundation, and what is the difference from this conventional static loading and what is the dynamic loading, that I will try to highlight, and what is the simplest method available for doing some analysis and for a dynamic loaded foundation. Here actually in static loading condition, most important part actually, because of the loading, how much pressure coming on the soil, that is important, that we have to find out that maximum allowable pressure should not your loading pressure should not exceed the maximum allowable pressure for the soil. But in dynamically loaded foundation, that particularly machine foundation, what I will discuss mostly, there actually that is not a problem. Most of the time pressure will be significantly low, but another important aspect which has to be taken care, that is actually that vibration amplitude during dynamic loading, and because of this frequency change of frequency, that machine will be vibrating at different amplitudes, and at lower frequency some, higher frequency some amplitude, and there may be some frequency where actually resonance will occur. We know that resonance means what, the natural frequency and driving frequency when coincides, then that become natural frequency, and at natural frequency your amplitude become excessively large. So, in the dynamic loading condition, that is the important, most important, that means you have to limit the amplitude. Like in the static problem, we are what is the maximum amount of settlement, and that settlement you have seen that it can be of 40 millimeter, 50 millimeter, 75 millimeter, like that different codes for different loading or different foundation type is recommended, and you have to design in such way that your settlement remain below that value. And here actually in the dynamic loaded condition, actually the amplitude is the displacement amplitude during formation is the important parameter, and that amplitude actually it will be much smaller, actually it is in the micron level actually, sometime not even millimeter. So, the fraction of millimeter. So, there are different methods are available actually to do the analysis, and again loading can, dynamic loading can be also different types, sometime it will be vertical dynamic loading, sometime horizontal dynamic loading, sometime rotational dynamic loading, and sometime rocking dynamic loading, like that will be there. So, because of that there are several parameters will be involved in it for calculating that amplitude, and perhaps I will try to very briefly try to introduce that in 4 hours, next 4 hours. Today I will just end here. Thank you.